All right, as you can see, this is going to be the 2017 AB Calculus free response. And I'm going to do problems numbered 1, 3, and 2. I understand that doesn't seem to make a lot of sense, but problems 1 and 3 are on both the AB and the BC test. So I'll do those together first. So all of you BC students watching this video, you watch this video, you find your problems 1 and 3, and then you'll have to stop this video and go to my 2017 BC Calculus free response question 2 video to get your third question in this set. AB students will do 1 and 3. I'll then wish the BC students farewell, and then I'll do your question number 2. All right? So let's start with question number 1. So for question number 1, they ask us, it says a tank has a height of 10 feet. The area of the horizontal cross section of the tank at height h is given by a function where a of h is measured in square feet. They don't tell us what shape our tank is. Okay, so this isn't a related rates problem like we normally would see where they tell us that the shape of the tank is an inverted cone or such. It just says we have a tank and the cross section of the tank h feet above the ground is given by a. And they tell us something about a. They say a is continuous and decreases as h increases. So I'm just going to draw a tank that looks something like, something like this. And it says the height of our tank the height of our tank is 10 feet. And a cross-sectional slice decreases as h increases. So my tank's not a cone. This side's not the same as that side. It's just a tank. Whereas I go up, the cross-sectional slice, right? The cross-sectional slice gets smaller as we go up. Now that slice is not a circle. It's just a slice. All right? Part A says use left-hand Riemann sums with 3 subintervals indicated by the data in the table to approximate the volume, indicate units of measure. So let's take a look at what we know about our tank. We know at 0 feet, 10 feet, at 5 feet, and at 2 feet, we know the square footage of a cross-sectional slice. At 0 feet, it's 50.3. At 2 feet, and I'm getting these off the table, at 2 feet, it's all the way down to 14.4. At 5 feet, it's 6.5. And at 10 feet, it's down to 2.9. All right? Now they told us our function is continuous and decreasing, our function a. And if we take a look at our function a, and we just kind of sketch it in here, we can make it continuous and decreasing, okay? Now it says use left-hand Riemann sums with 3 subintervals to find the volume of the tank. So this is number 1, part A. They want us to find the volume of the tank, right? The volume. Now, what do we know the volume is going to equal? Well, it's going to be the integral from 0 to 10 of the area. The problem we have, of course, is we don't know the area, right? We don't know the area function. They didn't tell us the area function. They gave us 4 values for the area function. So the best we're going to be able to do is approximate this. They asked us to use left-hand Riemann sums. So if we come over here, right, if we come over here and we draw in our you want to use left-hand Riemann sums. right, so those are our left-hand Riemann sums. So we're going to find our area based on the left-hand side of each of these intervals. And then, of course, we know the width of each of those. So right here, our width is going to be 2. Our height is going to be a of 0. We'll just go ahead and write that as a of 0. Now, what's our width here? Our width here is 3. Our height, left hand. So it's going to be this side. So that's going to be our height is going to be a of 2. How wide is this one? 5. And our height, left-hand intervals, is a of 5. So what do we get here? We get 2 times 50.3, right? Left-hand side, plus 3 times 14.4, plus 5 times 6.5. And if we do our arithmetic and work that out, we get 176.3 cubic feet. Okay. So that's our estimation for the volume of our tank. We indicated the units of measure. Part B says, does the approximation overestimate or underestimate? Well, we can look at our approximation, right? Remember, the interval, the function itself is decreasing. So if we look at our rectangles are too big, so we overestimated. Part B, we would say this volume is an overestimate because A of H is decreasing and we used left hand Riemann sums. All right, so that's part B. Part C says the area in square feet of the horizontal cross section H is, okay, so now in part B they're going to tell us, hey, I'm going to give you a function for the area. I'm going to give you a function now. And so in part C they say this is the cross-sectional area at height h. They're going to tell us a function. And they give us 50.3 divided by e to the 0.2h plus h. So this is now the function, and it says find us the real volume. Find us the real volume. So this is now, they've given us a function for the area. So the real volume would be the integral from 0 to 10 of this. Now, we can't do that integral by hand. We have to use our calculator. That's why it's on this question. And if we use the calculator, all we have to do is write this down. We get 101.325 338 cubic feet, right? So our actual volume was 101. Our estimated volume was 176. Clearly we did overestimate. Okay, clearly we overestimated. Now what's going on in part D, right? What's going on in part D? Well, D says water is pumped into the tank. Okay, so now we have water coming into our tank. When the height is 5, right? When h equals 5, the height is increasing at the rate. The rate means derivative. The height is increasing at the rate of 0.26 feet per minute. Using the model from part C, find the rate at which the volume of water is changing. So they want us to find dv dt, dv dt, with respect to time when h equals 5t. Okay? So how are we going to do that? Well, we need a formula for volume. Right? We need this is the formula for area. This is not the formula for volume. The formula for volume is going to be with respect to h, and that's going to be the integral from 0 to h of f. I got to change variables here, so I'm just going to pick x. You could pick any variable here you want. You can't have it be this variable. This says the volume at time 2 is the integral from 0 to 2 of this. Because the integral from 0 to 10 was the total volume, so the integral from 0 to 2 is going to be the height, the volume at time 2. The integral from 0 to 3 is going to be the volume at time 3. The integral from 0 to 6 is going to be the volume at time 6. So this is my function, but what do they want me to do with that? They want me to take the derivative of that with respect to t. Notice it's a t, not an h. So from here, we take the derivative of this side. Now we got to take the derivative of this side. That's the fundamental theorem of calculus part 1. When you take the derivative of the integral, they undo each other. So when we take the derivative, we get f. We put this in here. But we're integrating with respect to t. So this is an h. So we're going to get, by implicit differentiation, dh dt. We got to remember the chain rule. Now they want us to know, hey, they want us to tell them, what is this at time when h is 5? Well, we can do that. It's f of 5 times dh dt when h is 5. They told us dh dt when h is 5. So this turns out to be f of 5 times 0.26. We use our calculator to find f of 5, and we get 1.694419. dV dt, cubic feet per minute. All right. So that's the fundamental theorem of calculus, part 1. If that went too fast for you, watch the video again. It's not that big a deal. Back it up 3 minutes, watch that part again. Watch that part over and over and over till it makes sense. All right, so that's question number 1. Now, as I said, I'm now going to do question number 3 because 1 and 3 are also on the BC test. So I'm going to do 1 now, and now I'm going to do 3. And then we'll wish the BC kids goodbye, happy days, safe travels, whatever we want to wish them. And then we'll do our question number 2. BC students, your question number 2 will be on a separate video. All right, so let's take a look at question number 3. So that was question number 1. We'll go ahead and skip question number 2 for now. We'll look at question number 3. So question 3 has a graph, all right? They give us a graph of f of x. Sorry, f prime of x. All right. So we have a graph. And what do we know about our graph? Well, let's see. We know we have 6 units over here. And we have 5 units over here. Our graph has an x-intercept here at 5, 0. It has an x-intercept at 2, 0. It also goes through 3, 2. Has an x-intercept at negative 2, 0. And it goes to 6, 2. So this is our graph. This is our function. Okay. So we have a line segment here. We have a line segment here. We have a line segment here. And then down here, this might be a circle, but at least it'll be a curve. So we have a semicircle down here, right? So yeah, that looks terrible. Let's just do it by hand, it'll be better. So this is a semicircle, so this is negative 2 feet. All right, so this is our graph of f prime. This is x. All right. Now, what does it say? It says the function is differentiable on -6 to 5. We can see that. The derivative exists everywhere, right? That's the definition of differentiability. Something's differentiable. The derivative exists. It does at every one of those points. Remember, we're talking about f. Don't look at this and think, oh, that's a corner. You're right. F prime is not differentiable, but this is f. F is differentiable, so therefore it's continuous, of course. And f of -2 equals 7. We don't know what the graph of f looks like. We have no idea. But we know at -2, the graph of f, right, if we were graphing f, at -2 it goes through -2, 7. And we know the slope at -2 is 0. So our slope there is 0. Part A says find f of -6. All right, f of -6. Let's find f of negative. Now we know what f prime of -6 is. Actually, we don't because somebody mislabeled that. We know what f prime of -6 is, but we don't know what f of -6 is. But we do know something. We know this. If we integrate from a to b of f prime, the fundamental theorem of calculus says if I integrate from a to b of f prime, I get f of b minus f of a. That's the fundamental theorem of calculus. Well, why don't we, if we want to know f of -6, why don't we integrate from -6 to -2 f prime of x dx? Now, why did I pick those numbers? Well, I picked -6 because they asked for that one. I picked -2 because they told me that one. See, what's this going to equal? This, by the fundamental theorem of calculus, is f. F, the derivative goes away when we integrate. F of -2 minus f of -6. We know this. It's 7. We know this. It's the area under the curve. We know that, right? We can draw this. We know what the area under this curve is. The area under the curve is the base is 4. The height is 2. It's a triangle. So 2 times 4 is 8. So the area under the curve is 4. So this side right here is 4. F of -2 is 7. They want to know what is f of -6. Well, it looks like it's 3. So we're done. That's all we do. Now they also asked us in part A to find f of 5. So how are we going to do it? We're going to do the same thing. This time we'll integrate from -2, right? Starting here, we'll integrate from -2 to 5. That's going to be f of 5, the thing we want, minus f of -2, the thing we know. Now first we're going to have to find these areas. 1, 2, 3, base of 3, height of 2, so that's 6, but it's a triangle, so it's half of that, so that's 3. Radius is 2, so the area of the circle is 4 pi, but it's a semicircle, so we get 2 pi, but it's below the x-axis, so we write the area as negative. So be careful on that. So what is this piece right here? Well, it's the area from -2 to 5. So that's going to be -2 pi plus the area of the triangle. That's f of 5. We don't know that. We want to find it. Minus f of -2. F of -2 is 7. Bring the 7 over here. It gives us 10, right? There we go. That's part A. Okay? That's part A. Fundamental theorem of calculus. So I'm going to go ahead and erase this over here. Okay. We'll probably need those numbers in a second, but we'll remember them. Right? We'll remember them. So what does part B say? Part B says, when is f increasing? Justify your answer. Well, we know when f is increasing. The sign test, or the first derivative test, says f is increasing when f prime is greater than 0. Right? That's what they tell us. And if we take a look at this, right, we take a look at our graph, we can certainly tell when f prime is greater than 0. F prime is above the x-axis between -6 and 2, and f prime is above the x-axis between 2 and 5. So f is increasing on, right, on -6 to -2 union 2 to 5. Now we have to check the endpoints, right? Remember, it's increasing when the derivative is greater than 0. Is the derivative greater than 0 at -6? Well, at -6, the derivative is +2. So we are increasing at -6. Are we increasing at -2? At -2, my derivative is 0. That's not greater than 0. At 2, my derivative is 0. That's not greater than 0. At 5, my derivative is 0. So this is where we're increasing, right? This is where we're increasing. And it said justify your answers because f prime is greater than 0 on those intervals. Okay, what about part C? Part C says find the absolute min. Now, remember, f is differentiable, means f is continuous. Because we have the closed interval method that says if f is continuous, it will have an absolute min on the interval of continuity or at one of the endpoints of the interval of continuity. So we are going to have an absolute min because our function is continuous. So, what are we going to look for here? Well, if you remember the closed interval method, it says we want to test two things: critical values and we want to test endpoints. Okay, we want to test, those are the things we want to test. So, how are we going to do this? Well, is there any place, critical numbers, now remember what that means, f prime of x equals 0, or f prime of x fails to exist. That doesn't happen because our derivative exists everywhere. So where does our derivative equal 0? If we take a look, our derivative equals 0 at -2. Our derivative equals 0 at +2. Let's go ahead and spread these a little bigger. Our derivative equals 0. Those are our only critical numbers. Our endpoints are -6 and 5. So those are the values that we have to test. Now, how are we going to find f of x at any of those values? Well, we've already found f of -6. Right? We found f of -6. We discovered that f of -6 was 3. Right? We found out that f of 5 was 10 minus 2 pi. We already found those two. They asked us for those two. Now, how are we going to find f of -2? Right? Well, f of -2, where are we going to go to find f of -2? Well, they told us f of -2 was 7. So the only one we have left to find is f of 2. F of 2 is the integral from -2 to 2, right? Isn't that what that's the trick we used before. So we're going to integrate from -2 to 2 of f prime dx. That's going to give me f of 2 minus f of -2. I know what this is. This is -2 pi, right? Because it's the area of the semicircle below the x-axis. F of 2 is what we're trying to find. F of -2 is 7. So what do we get? We get 7 minus 2 pi. Now we're supposed to find what now? The absolute what? The absolute minimum. Okay, well, 3 and 7 are out, right? What's 10 minus 2 pi is like 6, right? 6.28. So 10 minus 6.28, 7 minus 6.28, that's going to be our absolute minimum, isn't it? So our absolute minimum is here. This is our absolute minimum. Now, where do we go from here, right? We get part D. Part D says for each of f double prime -5 and f double prime 3, find the value or explain why it does not exist. Okay. So, let's get rid of some of this. We'll make some room down here for part D, right? Part D says, tell me anything you can tell me about f double prime of -5 and f double prime of +3. All right? So, what's f double prime of -5 and what's f double prime of +3? Well, let's take f double prime of +3 first. +3 is right here. F double prime is the derivative of this graph, and that's a corner. So we know derivatives don't exist at corners. So f double prime of +3 fails to exist. But we have to show that. We have to show, hey, the limit as I approach 3 from above of f prime of x. The limit as I approach 3 from below of f prime of x. We can find both of these, right? And we're going to show these don't exist. as we approach 3 from above, we're on this line. We know what the slope of this line is. It's 2 minus 0, y minus y, over 3 minus 5. And we know that's negative 1. What do we get on the other side? We get 2 minus 0. We get 3 minus 2. Right? So this one is positive 2. And let's make this sign up. Let's get this off here. We said this was 2 over, this is negative 1, and those are not equal. Okay? Those are not equal. So f double prime of 3 doesn't exist. What about f double prime of 5? Well, that's just the slope here. We know what that is. We just did that one, right? I guess we haven't really done that, right? Because we did here, that's f double prime of positive 5. We want f double prime of negative 5. Well, that's the slope right there. What's f double prime of negative? Well, that's not a corner or a cuff, so we know this is going to exist, or a vertical tangent line. So what do we get here? We get 2 minus 0, y minus y, over negative 6, whoops, minus negative 2. So that's 2 over negative 4, which is negative 1/2, and therefore it exists. Okay? All right. So that takes care of problems 1 and 3. So BC kids, you can exit out of this video. Your problem 2 is on a separate video. AB kids, don't go anywhere. I'm going to erase this, and we're going to do our problem 2 right now. So what does our problem 2 ask us to do? We have a grocery store, and it opens, it has 50 pounds of bananas on display. 50 pounds of bananas on display. So this is number 2. When time equals 0, because that's when we open, we have 50 pounds. Okay, 50 pounds of bananas on display. Now, customers remove the bananas from the display table at a rate. So this is our remove rate. And that's f of t equals 10 plus 0.8t sine of t cubed over 100. And this is valid between when the store opens, times 0, to 12 hours later when the store closes. Okay? After the store has been open for 3 hours, we add bananas to the display. So after 3 hours, we add at the rate g of t equals 3 plus 2.4 ln t squared plus 2t. And this is after 3 hours, so this is from 3 to 12. Okay? And it said after 3 hours. Now, on these kinds of problems, it's always best, probably right off the bat, to just define these two functions in your calculator. Get them in there so in case, that way it's going to save you time down the road. Now, part A says, how many pounds of bananas are removed from the display during the first 2 hours? what is removed during hours 0 to 2. Okay. Well, how much bananas are going to be removed between the hours of 0 to 2? Well, we know the rate at which bananas are moved. These are bananas per hour. This is the rate at which bananas are removed. We want to know the amount, right? This is the amount. To go from rate to amount, we use the net change theorem, also known as the fundamental theorem of calculus. So if we want to know the amount of bananas that were removed, right, then removed is going to equal the integral from 0 to 2, because remember, that's a derivative, and when we do the integral, take the integral of a derivative, we undo the derivative. So rate per hour becomes not rate per hour anymore, it becomes the amount. So we're going to integrate from 0 to 2 of f of t dt. And here having that stored in your calculator is going to save you a lot of time. If you define that function at the beginning of the problem, it's going to save you an immense amount of time. And so we just plug that in, and the answer to that is 20.051175. All right, pounds of bananas. All right, so that's how many bananas were removed. Now, part B says, find f prime of 7, use correct units, explain the meaning of f prime of 7 in the context of the problem. Okay, so f prime of 7, that's the derivative of the removal rate, right? That's the derivative of the removal rate. So, are bananas leaving the store faster at time 7 or slower at time 7? Because we're taking the derivative of the rate. So we're finding the rate at which the rate of bananas is being removed. And I'm going to say those words again because those are the correct words. We know our bananas are being removed. Now the question is, they're being removed either faster and faster and faster. The longer the store stays open, the more people are buying bananas. There's a banana rush. Or they're being removed slower and slower and slower. When the store first opened, people were removing a lot of bananas. The rate was very steep. But now that the store has been open 7 hours, the rate has really slowed down. People are not removing bananas very fast. Versus over here, right? So, these are the two graphs we should have, right? Here, at the time the store opened, people were removing bananas, but they were only removing them at this rate. The derivative is the slope. Now they're removing bananas at this rate, faster and faster and faster. But now what else happens? Well, here they're removing bananas when we open at a slow rate, a fast rate, pardon me. Here, when the store's been open for a while, we're removing bananas at a slower and slower rate. That's what they want us to know. That's what this tells me. So one more time. This tells me the rate at which the rate of bananas is changing. That's what that tells me, okay? The rate at which the rate of bananas being removed from the store is changing. Now, how are we going to find that? Well, we're going to take the derivative of this and plug in 7, right? We're going to ask our calculator to do that because we have a calculator problem here. This is defined in our calculator. We're going to ask our calculator to take the derivative of this, just using the differentiation key. We're not going to do the derivative by hand, do the product rule and take all that time. We're going to ask our calculator to take the derivative of this, that's what they expect us to do, and plug in 7. And when we do that, we get negative 8.120. All right? So that's negative. Negative. What does that mean? It means the rate at which bananas are being removed is decreasing because the derivative is negative, so the rate at which bananas are being removed is decreasing. It's decreasing by 8.120 pounds of bananas per hour. So if we had 30 pounds taken away in the last hour, then this time we're going to have 30 minus 8.12 pounds of bananas being taken away. Now part C says, is the number of pounds of bananas on the display increasing or decreasing when t equals 5? Give a reason for your answer. Is the number of pounds of bananas? Well, that's going to be the removal rate right? That's our removal rate. And what are we going to do? We're going to take our removal rate, well, we'll just write it in the other order so the negative sign is easier to see. We're going to take our added rate minus our removal rate, the rate we're adding them, minus the rate at which we're adding them, minus the rate the customers are buying them, and we're going to see if this is positive or negative, right? So that's going to be G of 5, which we're going to find with our calculator, because we've put this into our calculator, minus F of 5, again, something we're going to find with our calculator, and we get here negative 2.263103. Now that's negative, right? That's negative. This is less than 0. So the number of pounds on display is decreasing. We're adding bananas back in, but people are buying them faster because the rate of the bananas on the display is negative, so it's decreasing. So the rate of bananas, which is the number of pounds of bananas on display, is going down at t equals 5 because the derivative is negative. Remember, these are derivatives, right? And when a derivative is negative, the function is decreasing. And they didn't ask us about these functions. They asked us about the number of pounds of bananas on the display table. How do we know if that function is increasing or decreasing? We take its derivative, we find it's negative, less than 0, so we say it's decreasing. Do you see what they're doing to you here? Do you see how they're playing with these derivatives that aren't necessarily a prime and making you think, wait, that's a derivative. I want to know about the amount of bananas, so I take the additional rate minus the removal rate. Those are derivatives. My derivative is negative, therefore the amount of bananas is decreasing. Now, in part D, so that, I'm sorry, that was part C, right? Part C. Part D says, how many pounds of bananas are on the table at time 8? How many pounds of bananas are on the table at time 8? So let's think about this. Store opens, we have 50 pounds. Now people have been buying our bananas for 8 hours. So they've been buying our bananas for 8 hours. Buying, negative. Bananas are leaving. And we know the rate at which they leave, but we also know how to make that into the amount at which they leave. If we integrate a derivative, we get the amount. That's the net change theorem. It's on the AP test every year. Plus We've been putting bananas on the table, right? But remember, we didn't start putting bananas on the table until the third hour. So we've only been putting bananas on the table between hours 3 and 8. Don't make that a 0 to 8. And we've been putting bananas on the table at the rate those are derivatives. So when I integrate those, I get the amount. So that's the formula that tells me the amount of bananas on the table. And when we do that, it's a calculator problem. We get 23.347 pounds. So 8 hours after the store opens, we only have 23.3 pounds of bananas left on our display. Okay, so that's questions 1, 2, and 3 on the on the AB test for 2017. Again, you can watch these as many times as it takes for them to make sense. Right? Don't just watch it once and go, I didn't get that. Okay, if you didn't get it, watch it again and again and again until it does make sense. You got this. All right, keep working.